Network Dojo.
In this video, we're going to be covering HASSO, or High Availability Stateful Switchover. So this is going to allow a pair of our controllers to essentially act as one in an active standby sort of pairing. That's not the type of pairing I mean, P-A-I-R-I-N-G. So there's like an active redundancy sort of a thing. And so the active controller is really doing all the work. It's the one that all the APs are going to terminate up to. It's the one that you're doing all of your configuration on, all the management type stuff is all happening on the active controller. And that standby controller is basically, it's staying synced up to what's going on the active controller, so that it can essentially mirror what's happening on the active controller in the event of a failure. And so if that active controller fails, the standby can almost immediately take over, oftentimes in a sub-second failover scenario, and just not miss a beat. It just takes over as that active controller. And in this case, the APs never drop their CAPWAP tunnels. Clients may not have to reassociate or reauthenticate, just depending on whether we're talking what type of HASSO that we have. But at the end of the day, it's almost as if the failure didn't happen. It's just a little blip on the radar, but everything just kind of keeps on going. There's not this massive failover that needs to happen like we looked at in the previous videos, where all of the APs drop their CAPWAP tunnels. They have to find another controller to join up to, reestablish that, and at that point the clients can reconnect. It's almost like the APs, the clients didn't even know that anything happened, other than maybe some packet drops or something like that. This feature is supported on our 5500, 7500, 8500, and WISM or WISM 2 AireOS controllers. I think the list has expanded since this code, like the 3500 support it now, but at least in 8.3 code, these were, I believe, the list of controllers that were supported with this feature. So we have two basic types of SSO. The first is AP SSO, and this is where the APs are unaffected by the failover. In other words, the CAPWAP tunnels never drop. And so the APs stay up, but the clients do not get the benefit of SSO. So the clients, after the failover happens, are all bounced and they all have to reassociate up. And this was what we got in the very first edition of this feature, which is back in 7.3 code. And then a few code revs later, we got client SSO, which adds to the AP SSO. And so now not only are the APs unaffected, they don't drop their CAPWAP tunnels, but the clients that are at least in a run state are unaffected by the failover. Clients that are not in a full run state do have to kind of start over their process. So if they're in the middle of the auth, or maybe it's like CWA or a WebAuth style WLAN where they're maybe in a WebAuth pending state, they would have to reconnect there. And this came about in 7.5 code. So pretty much everything that we do in any modern codes here benefits client SSO. So when we're running this, what really happens is all the configs become the same between the units, but there is a couple of notable exceptions in terms of configs that don't sync from the active to the standby. The active really becomes that reference point here. And so if the active and the standby controllers, when you're initially configuring this up and getting them to pair with each other, they will have separate configs on them, but at the end of the day, the active controller replicates this config down to the standby controller. But there's a couple things that don't push over. So number one, each controller has a unique redundancy management IP address. Each controller does have a unique redundancy port IP address. So a couple of these redundancy interfaces that we'll get into in just a few minutes here, those are unique. And each controller can have a unique service port IP address. So some IPs can be unique, but most of the IPs, like the management interface, the virtual IP address, all the dynamic interfaces, AP manager interfaces, all of those are synced from the active down to the standby. So let's take a look at these interfaces in more detail. So the first unique interface that we use for this HASSO setup is the redundancy port. So this is actually a separate, it's an interface, but it's also like the service port, where it's an interface that maps to a specific physical port on the controller. And so it's a separate physical port on the controller, And this is our primary means of syncing information between our controllers. And so what we want to do is we need to connect the redundancy port of controller 1 to the redundancy port of controller 2, or the active and the standby. And so across this redundancy port are all of the syncings of configs, client states, all that data is syncing across the redundancy ports. We also have keep alives going across the redundancy ports as well. One of the requirements of the redundancy ports on the active and standby controllers is that they do need to be layer 2 adjacent. And ideally, you actually physically connect them to each other. So it's just a single Ethernet cable from the redundancy port of controller 1 to the redundancy port of controller 2. It doesn't have to be that way. You can have intermediary switches and networking devices between the two, but as long as they're layer 2 adjacent, that's the important part there. So the IP addresses that we use on these redundancy ports are non-routable IPs. They're 169.254 addresses. And the addresses are actually derived from the redundancy management interface, which is, we'll talk about that one next. And we do have a requirement in terms of latency between it. So we have these keep alives that are going across here. So the keep alives will have a timer. I think it's 100 milliseconds by default. And so the latency between the two devices on the redundancy ports cannot exceed 80% of the keep alive timer. That keep alive timer is adjustable, and so if we do have higher latency because we are maybe spanning longer distances between these two devices, we can increase that keep alive timer to get it up above that 80%. In most cases, I mean, there's an upper limit. I don't know if it's like 400 milliseconds might be the maximum keep alive timer, but the latency cannot exceed 80% of the keep alive timer is one of the design requirements there. So the second interface is that redundancy management interface. Now this is an interface that is going to be shared on the same subnet as the management interface of the controller. So if my management interface is on VLAN 104, my redundancy management interface is automatically also on VLAN 104. It is not configurable. It just always uses the same VLAN as the management interface. But it does need to be a unique IP address, and it's unique on both controllers, because this is another one of those interfaces that there's going to be communications between the active and the standby switch on. So this interface becomes almost a secondary interface for keep alives to help detect different types of failure scenarios. We need to try to figure out, if that redundancy port, if that link goes down, is it because one of the controllers truly went down, or was it just something in the network went down, but both controllers are both up? So now we have this redundant connection between the two boxes that we can also do a check between them to see, okay, are both of them still up, or is one of them truly down? We would know the other one's truly down if we lost, keep alives on both the redundancy port and the redundancy management interface. Whereas if you lose it on one, but the other one stays up, we know both boxes are up and we don't have an accidental failover process here. Another use for the redundancy management interface is for testing connectivity to the default gateway. We can have failovers occur if the active controller can't talk to its default gateway, but the secondary can. And so that's another thing that we use. Can they talk to their default gateway, and could that cause a failover process? Also, that standby controller is going to use this interface to source management traffic like syslogs and NTP-based information. So let's actually just kind of draw this out here and show you, what this kind of looks like, and it might make a little more sense here. So again, we have two controllers here. So I'll call it, well, I won't call it active standby. I'll just call it controller 1, controller 2. And then we have a second controller here. So again, we have a couple of different interfaces going on, but let's say we have our switch network down below, and this could be the same switch, could be redundant switches. It just represents the regular network here. So we should have, ideally, this direct connect between controller 1, controller 2, and this is the redundancy port. And again, this is where all the syncing happens. Across the redundancy port, we also have heartbeats flowing back across this redundancy port here. And then, we have distribution ports that go down here. So we have the redundancy management interface is going to be using one of your distribution ports. Should be the same distribution port that your management interface is using. So we have redundancy management interfaces down here, as well as the regular interfaces on our box. And so on the redundancy management interface, we're also doing heartbeats here. And it's heartbeats between the controllers. So redundancy management interface on controller 1 to redundancy management interface on controller 2. There's also these, the default gateway that lives somewhere down here. It's doing a default gateway check. As well. And so this is sort of the basic setup that we have in terms of these redundancy interfaces with our box. And so as long as everything is up, we would configure, say, controller 1, we configure that one to be the active switch. So we'll say this one's the active, which would then make controller 2 the standby. So the active controller, again, that's the one that controls what things really are, and that's the one that's actually terminating CAPWAP tunnels, and that's the one that you would access the GUI on and do all your configurations through. So that's essentially syncing all of the information across the redundancy port over to the standby device. And so the standby device is just keeping tabs on everything. It's accepting all these synced information. It's doing heartbeats just to try to check, okay, is controller 1 still up? Is controller 1 still up? Is controller 1 still up? Over and over and over. It's also, potentially, because we can turn this on or off, checking the default gateway. So the default gateway check is an optional configuration, but I believe it's on by default. To see, can I talk to the default gateway? Can I talk to the default gateway? And controller 1 is doing the same thing. Is controller 2 still alive? Can I talk to the default gateway down here? And so as long as everything's up and running, controller 1 stays as the active controller. So, in terms of failovers, there's a number of ways that a failover could occur. So let's say that controller 1 goes down. Well, when controller 1 goes down, if it goes hard down, we would lose a link on the redundancy port here. And if this was a direct connect, we would lose link on the redundancy port on controller 2. And that's an immediate notification that controller 1 may be down, as opposed to waiting for heartbeats to time out. Not that a heartbeat timeout is exceedingly large. Again, it's 100 milliseconds by default, so it's a tenth of a second. But we say that tenth of a second, and what it's going to do is it's going to do the heartbeats across the redundancy management interface. If those are also down, which would be the case if controller 1 just went hard down, controller 2 determines, okay, controller 1 is down. I take over as the active controller, and all of a sudden, all the IPs that used to be on controller 1 are now alive on controller 2. I believe it does some gratuitous ARPs to essentially let the switch network know that, hey, this MAC address lives over here now. So the wired network updates its forwarding tables, and everything is forwarding to controller 2. APs and clients are really none the wiser. But let's say that controller 1 actually didn't go hard down. Let's say that we have just individual link failures. So for instance, we could have this redundancy link go down. So if the redundancy port link goes down, we stop hearing heartbeats here, or potentially the link just flat goes down, depending on if we have an intermediary device in here or not. But again, that's why we have this secondary check, because controller 1 is still up and running. It's just we have a problem with the link between controller 1 and controller 2. So controller 2 is going to do the heartbeat check between the redundancy management interfaces. It's going to see that controller 1 is still responding on the redundancy management interface. Controller 1 stays the active switch. Controller 2 stays in a standby mode. And it's actually in a bit of a limbo state, because now it's not getting the sync over. And so we can't have a stateful switchover until we repair the redundancy port. But if eventually controller 1 actually, if we started in the state and then eventually controller 1 did go hard down, we would detect it with these heartbeats, and then we should be able to fail over to controller 2. Controller 2 is active, but it would not be graceful at all. Because we didn't have the syncing taking over. And so I believe the failover should still happen, but like I say, it would absolutely not be graceful. this link goes down, but the redundancy port stays up. So controller 1 is still physically on, but for some reason, whether it's the link goes down or it can't talk to its default gateway, and obviously the redundancy management heartbeats would probably be failing as well. And so in this case, we still have the redundancy port up, and so we're still having heartbeats, but we should see that we lose the access here, as well as controller 1 should detect that, you know what, I can't talk to my default gateway anymore. And so if we have the feature on where if it knows that it can't talk to its default gateway, but controller 2 can talk to the default gateway, because it's the same VLAN, it's the same default gateway for both of these, on the redundancy management interfaces, we can initiate that failover. Because if controller 1 can't talk to its default gateway, it's essentially dead in the water anyways, right? So controller 2 can take over as the active switch in that type of a scenario. And so there's a few different ways that we can cause failovers to happen. And this is why we have the two interfaces in the checks that we do, so that we can detect, is this a real failure? Because what we really don't want to have happen is to have controller 1 acting as the active switch, and then controller 2 thinking controller 1's down and having it also go active. And then all of a sudden you have two devices using the same IPs. That's going to be disastrous. So that's kind of why we have the design the way that we do. Okay, so hopefully that kind of makes it clear that the two interfaces that we have going and sort of the purpose of those two interfaces and how it plays into the syncing process and failure detection processes. So a note about the WSM2s. So the WSM2s, these are not separate physical controllers. These are line cards that would go into something like a 6500 series chassis-based switch. I don't even know if it's supported in anything besides a 6500, but definitely a 6500 chassis-based switch can support these WSM2 line cards that are controllers within a chassis. So with these, we don't have physical ports like we do on any other of our controllers. They have just sort of logical ports that connect to the back plane of the chassis. And so when we want to do HA-SSO with the WSM2s, so we need two WSM2s. So we need the redundancy at the physical level, but with two different line cards here. We can either have two WSM2s in a single chassis, or we can have one WSM2 in separate chassis of a VSS pair. So a VSS pair, I can't remember if I really have talked about this one before, basically takes two 6500s and creates them to be one logical device. So it's almost like one switch that are just connected across a couple of 10 gig links, but it is operating logically as one device. And so when you look at your show run, it's got the run and config, and it includes all the configs of all the ports on switch 1 and all the configs of switch 2. It's really both from a control plane and a data plane. They're shared, which is separate from like Nexus doing their virtual port channel type stuff, where it's actually separate control planes, single data plane here, but irrelevant. So it's just two 6500s working as one logical device is what a VSS pair is. And so you can have one WSM2 in one of the chassis and one WSM2 in another chassis, but it has to be in a VSS pair. It can't just be one standalone 6500 here, one standalone 6500 here. That one doesn't work. So that's one of the requirements there. So the WSM2 is, rather than having a redundancy port, because there are no physical ports in here, it has something called a redundancy VLAN. So the redundancy VLAN replaces the redundancy port function. So the redundancy VLAN would have an IP address on both devices, just like the redundancy port has an IP address on both devices. You do have to create the VLAN. It doesn't automatically create just by saying, hey, redundancy VLAN's this. Well, you have to define the VLAN on the switch and then call it out as the redundancy VLAN in your WSM configurations. So design guidelines for this. It should be an unrouted VLAN, meaning that there are no SVIs on the switches for it. It should just be a VLAN with no layer 3 interfaces at the switch level. You'll get the IPs at the controller level there. It only needs to exist where the WSMs are. So if it's a single chassis 2 WSM setup, the VLAN only needs to exist on that switch. If it's a VSS pair, creating it within the VSS automatically makes it active on both switches, so it doesn't have to be available anywhere else in the network. And then you create the redundancy VLAN like any other. You reference it in the high availability config.